Our speaker for this evening is Spencer. He has been a member now of Amateur Astronomers for a couple of years. He's a high school student. He's given presentations here before, and with that, I'm just going to turn it over to you.
All right, hello everyone. Can you hear this well?
Yeah.
Okay. Thank you, Mary, for the introduction. For those of you who just walked in, my name is Spencer. I'm a rising senior at Scotch Plains Family High School. I've been a member here for almost 3 years now, I think, so it's been a while. And tonight, my presentation is on special relativity, the physics of space and time. All right, so before we start, we got to talk about Albert Einstein. I'm sure most of you already know who he is, so this will be a quick recap. There's him right there with his famous picture of his tongue out. He was born on Pi Day, which is pretty ironic, on March 14, 1879 in Germany. In 1905, he published his Miracle Year papers, and those included special relativity, which we're talking about, and part of that is his famous equation, E equals mc squared. In 1915, he published the general theory of relativity, which challenged Isaac Newton's previous view of the universe, where gravity is absolute and we know everything. But Einstein changed all that. In 1921, he was awarded the Nobel Prize in Physics, and it wasn't for general relativity or anything with gravity. It was actually for the photoelectric effect, which I'm not covering in this talk, but something worth looking up. Then 1933, he left Germany, came to the United States, and eventually taught at the Institute for Advanced Study in Princeton, where he ended up spending the rest of his life. So what is special relativity? So as I mentioned, it was proposed in 1905 by Einstein, and it describes the relationship between space, time, and not yet gravity, that's general relativity, between space and time at relativistic speeds, which means super close to the speed of light. And I'll just use c for the speed of light. And it challenges the way that we usually think about time, distance, and motion. This is the most important part. It applies only to non-accelerating or inertial reference frames, as indicated by the special and special relativity. So what that means, if you're standing still, you're not accelerating. If you're walking at a constant speed, you're not speeding up or slowing down. That's not accelerating. So that's what this applies. So before we talk about the consequences of special relativity and what it actually means, Einstein says these two things are always true. That's what a postulate is. So his first one is the principle of relativity, and that says that the laws of physics are the same for all inertial frames of reference. So if I'm walking at a constant speed and I'm not accelerating, the laws of physics are the same for me as they are for all of you who are sitting still and not accelerating. And that's pretty reasonable. I mean, he's not demanding anything too crazy. Then is the universal speed of light, and that says that light is always traveling at about 300 million meters per second. So pretty fast. It's not infinitely fast. Light does have a speed, but super duper fast, and it's always the same. No more, no less. So what are the consequences of these? First, if the speed of light is always the same, then some other variable has to change. So these are the three consequences. So first is the relativity of simultaneity, and that means that two events that happen at what feels like the same time might not actually be happening at the same time. Sounds confusing now, I'll get to it a bit later. Time dilation, which a few of you have probably heard of, it's probably the most famous one of these. And that says that moving clocks will tick slower than ones that are stationary. And then length contraction, where moving objects shrink. So first, the relativity of simultaneity. So we usually think of now as a universal thing, a universal instant in time, the same for me as it is the same for Mary. But two events that happen at the same time might not be at the same time. So what's now for this fairy over here might be now for my friend Alex over here. Might be different. So here's an example. Let's say we have a train, and this train is moving very, very fast. We'll say it's moving super close to the speed of light. So we have Alex on top of the train, and a fairy floating above it. From the fairy's perspective, let's say that as the train passes her, there are two lightning strikes, one in the front of the train and one in the back. The lightning strikes are equal distant from where the fairy is, so she's halfway between them and she sees them at the exact same time. But if we go from Alex's perspective, he's going super duper fast. So as the first lightning strikes, he sees the light from the first strike first, from the one in front of him. Because since he's moving really, really fast on that train towards the lightning strike over here, he's going to see that light first. Because remember, light doesn't appear instantly. So the light from that exit sign over there, it's coming to my face, but it's not instant. It takes some time. Next is time dilation, and this is probably the most famous part of Einstein's special relativity. Here there's a little bit of math, but I've made sure it's all stuff you could learn in high school. So those of you who haven't gotten there yet, I'm sorry, but everyone else, you'll understand this. So this is some simple equations. We know that velocity is equal to the distance over time. So what does that mean? Velocity is pretty similar to speed. So if you're driving your car, you see a speed limit, 35 miles per hour, that's how fast you can go. And where we have the distance over the time, that could be anything. It could be meters per second, miles per hour, kilometers per second. It could be millimeters per microsecond, anything like that. Then, if we do some multiplication, you can rearrange this equation. You get that the distance is equal to the velocity multiplied by time. And since the speed of light is a constant, the speed of light would be v, but we would write it as c because that's the constant for speed of light. And then when the time changes, we get time dilation. And then when distance changes, you get length contraction, which we'll get to a bit later. So here's another example. We have Alex on the train again, and the train's still moving very, very fast. So we'll ignore the front of the train here. And Alex, he's at the top of the train, and right across from him is a mirror. And what he's going to do, he's going to shine his flashlight at the mirror. And what happens when you shine a light at a mirror? It comes right back to you. It's pretty common sense. So light goes back to him. That's from his perspective, from inside the train. But if we take the fairy's perspective now, when Alex is still moving very fast, when he shoots the light, the train starts to move away. So the fairy, she doesn't see the train right here. She sees it moving as the light is being shined. So now the train's over here, but that light is still approaching the mirror. The light doesn't turn away from the mirror. But now, the mirror isn't over here anymore. It's over here. So the light takes more of a diagonal path, kind of like this. And then the same thing happens again. Alex moves again on the train, and then when the light bounces back, it's in a diagonal path. We can actually see this in real life. It's a pretty easy thing to demonstrate. Got my phone right here. So if I move this flashlight up and down, moving up and down for you guys, up and down for me, because I'm stationary. As I start moving, I'm going to keep moving up and down. Starts to take a diagonal path for all of you. That's pretty much what's happening in this train example. All right, so now we can do a little bit of math. It's not too much, nothing crazy, but it helps with some examples later on. So let's say that the distance between Alex and the mirror on the train is 1 meter. So then when he shines the light to the mirror, the time that takes, we'll call it a tick. And then the time the light goes from the mirror back to Alex, we'll call it a top. And we'll call T naught or T0, and that's the time taken for the tick tock of a stationary clock. So when Alex is not moving on the train, that's how long it takes. And we could say that T naught is the distance over velocity, and that's equal to 2 over c. So remember, we have velocity equals distance over time. If you rearrange that equation, you get time is equal to distance over velocity. Remember, the velocity of light is always the same, c, 300 million meters per second. So that's where we put the velocity, we put c. And for distance, we know that the time it takes the light travels down the mirror, which is 1 meter, and then back up to Alex, which is another meter, so 2 meters. So remember this, T naught is equal to 2 over c, because that will come in handy later. And T naught is the time taken for the tick tock of a stationary clock. So here's a better example. I got rid of Alex because kind of annoying to keep copy and pasting him in here. So this is what we had before. It's just showing that there's a diagonal path followed by the light. And this is on a train. We'll say it's moving at velocity v meters per second. So that just, the v could mean anything. It could be 1 meter per second or 100 million meters per second. It doesn't really matter for this example. And remember this equation, distance is equal to the velocity times time. So the distance that the train travels is equal to the velocity of the train times the time for a tick. And then the distance that the light travels in the time of a tick will be equal to CT, as shown right there. And then we have to remember that the distance between these mirrors is the distance between Alex and a mirror, that's 1 meter. So we'll put that right there. So anyone noticing a certain shape going on over here? Something we could do some math with? Yes, it's a right triangle. So what can we do with that? Everyone's favorite, Pythagorean theorem. So all you have to do, you do CT squared equals VT squared plus 1 squared. And I'll save all that boring simplification. And we'll get that the time for a tick is equal to 1 over the square root c squared minus v squared. So that doesn't mean too much for now. It's just a silly equation, but we'll get to what it actually means. So what we have is the time it takes for a tick of a moving clock. But that's not what we want to know. Remember, a tick is just when you shine the light to the mirror. We want to know how long it takes to go to the mirror and back to me, right? So all we have to do is multiply it by 2. And then we get lowercase t, which is just equal to 2 over the square root of c squared minus b squared. And little t, that is the same thing as a tick tock, not of the stationary clock, that's a t0. And then we could simplify this a bit. We'll take out a factor of 1 over c. And why are we doing that? Does the 2 over c that I mentioned earlier come in handy? Yes, it does. So what we can do, we can simplify that equation to this, which is basically saying that the time for a tick-tock of the moving clock, a lot of rhyme in there, is equal to the time of a stationary clock over that piece of the equation. And then we could simplify this. T equals gamma T naught, where gamma is this right here. And what gamma is, it's called the Lorentz factor. So we can do an example of this. I wasn't just making you guys do math for no reason. So let's say it takes Alex 15 minutes, or about 900 seconds, to sing the ABCs 10 times while stationary. How long does it take for him when moving 70% the speed of light? So it's a very realistic scenario. So what we could do, we could take gamma, remember gamma's up here, and he's moving 70% the speed of light, or 7/10, multiplied by c, so 7/10 c. And the bottom right there, that's still c, that's also the speed of light. So we can simplify this, and we get gamma is equal to 1.4. Then we go back to that top equation up there, and we get that the time for a tick-tock is equal to 1.4 times 900. And that is 1,260 seconds, or 21 minutes. So what this has proven is that when you're moving, time moves slower for you. So see, when Alex is stationary, it takes him 15 minutes to sing these ABCs. But when he's moving super duper fast, 70% the speed of light, it'll take him 21 minutes. So it's very interesting. We'll do one more example. This is a bit more extreme. So a photon, which is a light particle, well, not really a particle, it's a wave and a particle at the same time. So that's another talk. And that travels at the speed of light. So let's plug this into the same equation. We have gamma again, and the velocity of a photon, as I said, the speed of light. So we get c. But c squared over c squared, it's just 1. We get 1 over 0, which in math you cannot do. It's not allowed, illegal math. So I put this into a graph just to see what it looks like. And as you can see, all the way up. And what this is saying is that for a photon, time does not pass at all. So what I like to say is, instead of getting Botox or any age reversing things, just become a photon. Time doesn't pass at all. And this was actually seen in real life. So there was the NASA twin experiment in 2015 where NASA launched Scott Kelly to the space station and he spent 340 days there. And his brother, who is actually a US Senator, he stayed on Earth. And they were twins before this experiment. While Scott was traveling 17,000 miles per hour on the ISS, his brother was staying on Earth. And remember, the faster you're moving, the slower time will pass for you. So when he came back, Scott was a few less milliseconds old than Mark. So they're no longer twins. And the last consequence of Einstein's special relativity is length contraction. And that's where a moving object appears shorter in its direction of motion. And this always happens every single day. So if you're watching a car go past you, it looks a little bit shorter than it should be. You don't notice it because maybe it changes a couple nanometers. So nothing too noticeable on our scale. And what this shows is that space and time are connected. As time gets longer, time dilation, distance will get smaller, which is length contraction. So here's another example with our train. It's again moving very fast, and Alex is of course on top of the train. From the fairy's point of view, as the train goes past her, she sees it shrink a little bit. And this is much easier to explain with math. So what we'll do, we'll say the train is moving past the fairy at half the speed of light, or 0.5 c, passing by her in 666 nanoseconds from Alex's point of view. So we have distance equals velocity times time, and the distance, or the length of the train, is equal to half the speed of light times the time it took for the light to pass the platform. And then we get that the length of the train is 99.83 meters. Makes sense so far? So that's from Alex's perspective. Now, past the ferry, the train is still moving at the same speed, still moving by her in the same time. Now it's from a different perspective. And what we have to do, we use this new equation up here. It's pretty much the same thing as the time dilation one. I just cut out all the boring math part. So we use gamma again. We use the velocity right up here. And since it's moving half the speed of light, it's 0.5 c. Then we get that gamma is equal to 1.15. So what we can do now, we do the length of the train while it's moving from the moving perspective. It is the length of the stationary train divided by gamma. So what we do is 99.83 divided by 1.15, and we get that the train from the ferry's perspective is only 86.8 meters, when from Alex's perspective, it was 99.83 meters. So it's much easier to explain in math, as I said, because you don't notice this every day, because unless you're moving at half the speed of light, but I don't think any of you are that fast. So what does E equals mc squared actually mean? This is probably what you were wondering when you saw the title of the slideshow, special relativity, of course. So E is energy, M is mass, and C, as I already mentioned, is the speed of light. And C is very, very big. 300 million meters per second. And remember, in this equation, C is squared. So since C is squared, that means 300 million squared. I don't know what that is, but it's very big. And what it's saying is that even a tiny amount of mass will give you a massive amount of energy. Because when you're multiplying the speed of light squared, 300 million squared, by even a tiny number, it's still going to give you a super big E value for energy. And because we can set energy and mass equal, it shows that energy can become matter, and matter can become energy. It's kind of a weird thing to think about, but it's been proven a couple times. So this actually explains how the sun gets its energy. There's super tiny masses of hydrogen, which is the first element on the periodic table, and they smash together in a process called nuclear fusion, and they create helium, a large amount of energy through nuclear fusion. So even though these hydrogen atoms are super duper tiny, since E equals mc squared, their tiny masses can convert into a super large amount of energy. That's why the sun is a huge furnace in our sky. This is kind of how fusion works. I didn't want to do too much here, but these two hydrogen atoms will come together, they release the neutrons and energy and form helium. And E equals mc squared is actually the basis for atomic bombs, nuclear energy, particle accelerators, and plenty more things. So here's an example. We have 1 gram of mass, so that could fit in your hand super easily, and that can release the energy equivalent to 20,000 tons of TNT, which is a lot of TNT. It causes a lot of damage. And there, of course, is an atomic bomb blast. See how powerful it is. Let's do it one more time. So as an object moves faster, its energy increases, and so does its mass. The closer you get to the speed of light, the more energy you need, which makes sense. This isn't the best example, but if you start running, the faster you get, the more tired you're going to get, the more energy you need. And nothing with mass can reach the speed of light. It would need infinite energy, except for one man, of course, Flash. But no, in real life, no one can get that fast. Oh, there you see. And a lot of you have probably heard of general relativity. That might be more talked about than special relativity. That's the one that talks about black holes, all that stuff. So we'll do a quick comparison. So special relativity. This is probably the best graphic to explain it. It has the clock that I was talking about, the light clock that shows the diagonal path. And that's a satellite orbiting around the Earth. So pretty much what I was talking about before. And then general relativity that deals with the warping of space-time. So first, special relativity. It was published in 1905. Non-accelerating objects only. So again, that's if you're stationary or you're moving at a constant speed. So you're not speeding up or slowing down. And it does not deal with gravity. It deals with time dilation, length contraction, simultaneity, and of course equals mc squared. General relativity, on the other hand, was published in 1915, so 10 years later, and it deals with accelerating objects, deals with gravity, and of course curved space-time, black holes, gravitational waves, and the expansion of the universe. So what is special relativity actually used for? Well, GPS. If we didn't know about special relativity, we would not be able to use GPS at all. So satellites orbit the Earth close to 14,000 kilometers per hour at about 20,000 kilometers above the surface. Depends on what type of satellite, but some of them do. And since they're moving super fast, faster than we are on Earth, the clocks tick slower due to time dilation. So remember, the faster you go, the slower time ticks. Also, in general relativity, this is just a side note, the stronger gravity is, the slower time moves. I'll get to that a bit later. The difference between the time on the satellite and Earth is only about 38 microseconds each day. But this can add up. That can mean a couple kilometers of shifting in your GPS. So when you're on your way to this observatory tonight, if we didn't have special relativity, then who knows, could have been 3 kilometers off and ended up in Weston. And of course, special relativity in pop culture. So probably the most notable is Interstellar in 2014. And near the black hole Gargantua, there was a planet where the astronauts went to, and 1 hour on that planet was about 7 Earth years. So that just shows how different time can be in different places. If you haven't seen this movie, I recommend it. It's very good. Then another one, a little bit older, in Planet of the Apes from 1968, there was some astronaut who went on a journey, and he was going at fast speeds, of course, and then he came to Earth, and he saw that his whole world had changed. So he had the Statue of Liberty in the water. I don't know if that's actually going to happen in the future, but maybe. And yeah, he came back and centuries passed. So conclusion. Space and time are not absolute, they're relative, as indicated by special relativity. The speed of light is the universal speed limit. Can't go any faster, can't go any, well, you can go slower, light can't go any slower. And it replaces our everyday assumptions with more odd truths. So you think that when a car drives past you, it's the same length as it is for the person inside the car, but really it's a bit shorter for you. But you don't notice it, of course, even if you really look, so don't claim you do. And it's not just a theory, it's contributed to important technology like GPS, particle physics, space exploration, and plenty more. Okay, and that's it. Thank you. Any questions? Yep. A little bit. That's when I was talking about land contraction. It's
Yes, excuse me, Spencer, repeat the question because the people like online can't hear.
he was asking if it deals with the Doppler effect. And for those of you who don't know what that is, that's if you have a wave of light going past you and it goes off into the distance, it will start to shift more to the red spectrum. I don't know how related it is, I'm sure somewhat, but I can't answer exactly. I'm not Einstein, so.
Anybody else?
Any other questions?
Check with the people online.
Any questions online?
No question, Spencer, but that was an excellent talk. Perfect level for the audience. Good
Thank you.
job.
Thank you.
Thank you, Spencer. And I meant to mention a couple of things. For the future, we are planning for an astronomy day in 2026. So Saturday, May 16th, tentatively, that's our planned date. Okay. And also, if you would like to make a donation to our organization, there is a donation box in the back on top of the sales desk. It's yellow. It's a yellow box if you'd like. Okay. All right. I don't know if anybody has any other questions in general. Hopefully, we've got something to view in the observatory, in the telescope. I don't know. I haven't been up there yet. Has anybody been up there yet?
It's clear.
Okay, it's clear. So, all right, go and enjoy. Thank you so much for coming. We hope you come back again. We will be here next Friday, okay?
Thank you.
John, you're, yeah. What's the web versus the big guy.